300,034,974,000 tests carried out across the UK, excluding Northern Ireland.
Keep hearing
Of
the
these,
numbers.
78,991 people have tested positive. 20,101
numbers.
are currently hospital in Great Britain.
We don't know what the numbers mean. For the last
Sadly,
time,
9,875 people have now died, an increase of 917 in yesterday.
where is the number station?
The numbers are real.
They've always been real, Mason. This isn't a game. We face annihilation unless you cooperate.
And we all know how that song and dance goes. Today's video is about the numbers, Mason. What do they mean? And how you, Mason, yes, you may be misled by the data. Let's start by having a look at the graphs on the screen right now. Would you say these two graphs are the same? What about these two charts? Or this scale? Or these? Or that one? Or those? Yeah, they are. Same, but different, if that makes sense. The logarithmic function recently has gained infamy because of the COVID-19 pandemic. I think because of that, in the first half of the video, we must use examples to explain the log function and its benefits, with studies dating back to about a century ago. And don't worry, there's not going to be too much maths. You don't need maths to understand the video. And in the second half, we're going to explain its drawbacks and pitfalls, again with examples. And of course, for your viewing pleasure, all the sources I use will be in the description below, and I encourage you to have a look at some of them for yourself. Now, according to the Lexicon of All Human Knowledge, Wikipedia, in mathematics, the logarithm is the inverse function to the No, I'm just kidding. All right, here's what you need to know for the video, and essentially anything you need to know to interpret these logarithmic graphs. This here is a logarithm of base 10 scale, it's the bottom, and how it maps to the linear scale on top of it. As you can see, the more and more we extend the logarithmic scale, the more and more the arithmetic scale becomes compressed. Expanding the logarithmic scale by just one value from 2 to 3 will expand the arithmetic scale from 100 to 1000, and so on and so forth in factors of 10. This is because this is a logarithm of base 10 scale, which can informally be represented just as log x. On the other hand, the natural logarithm inverses the exponential function and is therefore of base e for exponential. The graphs of the general forms of these logarithmic functions give us some insight as to why we observe gently sloping COVID-19 curves, but are constantly warned about an exponential growth in the number of infected patients. Now, I appreciate it's a little bit difficult to see, but the green one is log base 2, blue one log based exponential, and the red one is log base 10. Intuitively, the same idea as before, the idea of having a larger base causing greater compressions of larger values is translated in our general form graphs. Finally, and most importantly, this is Fisher's handy-dandy guide for interpreting logarithmic charts from his 1917 publication on ratio charts. And that, ladies and gentlemen, is basically all you need to know to understand and interpret these logarithmic data reasonably quickly by inspection. Let's talk perks of the logarithmic function. Firstly, in academia, in regression analysis, it's a very quick way to help us achieve approximate homoscedasticity with our data, or to be able to obtain normally distributed relationships. Homoscedasticity is a Gauss-Markov assumption we need for an efficient linear regression estimation, and the latter arises naturally because a lot of relationships we observe are actually log normal. Incomes are the archetypical example where almost all of the population have their incomes typically log normally distributed. And if you've ever read a study with an income variable, it's almost guaranteed that they're using a log income variable. Let's pull up the 2008 study on marginal utility of incomes by Layad et al. They found that plotting real happiness against raw household income is not a nicely distributed normal relation. However, when plotted against a log of the household income, we get this beautiful, stunning, bountiful, normal linear relationship. Look at it. Love it. Don't stop looking at it. don't stop loving it. In a field like economics, where the majority of our experiments have to be natural, tools like this are essential for robust and clear analysis. Even going one step further and using log-log relationships is very useful. When differentiated, these log-log relationships are interpreted as the elasticity. So observe this graph. It's almost impossible to visually derive anything useful from the first third of the graph, but much of the policy discussion and criticism has been to do with the start of the outbreak and the speed of government responses globally. Now have a look at this one. The logarithmic scale is much easier to analyze for the growth rate of the pandemic if you understand what it means. Furthermore, even the y-axis scale is actually much more interpretable until around March 8th, as opposed to the linear interpretation, which has divisions of 2.5 million. It just works. It just works.
16 times the detail.
There are a lot of data that in a linear fashion show an exponential growth rate or an exponential decrease. Just look at the US government debt. Up to 1985, the second graph is actually much easier to visually interpret, and we can infer information about the rate of growth much more easily. Using Fisher's handy-dandy guide, the rate of growth here up to 1985 is positive and we'll say largely uniform over time, maybe increasing if you're really going to stick your eyeball in there. And what does this tell us? Well, the first bullet point says that this means we know that the statistical magnitude it represents is increasing at an almost uniform rate. Let's try another one, but now applying it to the number of COVID-19 cases. The sixth point tells us that up to and around February 15th, we had a much faster growth rate of cases globally than after April 20th. However, if you try to draw insights from the linear representation, you might actually mistakenly arrive at the opposite conclusion. So why are media outlets outraged and up in arms about the logarithmic function? Mind you, the same media outlets that by default present this data in a logarithmic fashion. Well, as always, it's all about the numbers, Mason, the numbers! The first reason is due to how the public perceive this information. The second, much less discussed reason, because maybe media outlets think government big-brained, public crayon munches, political capture, and incompetence. Behavioral economics has proven that framing information is incredibly important to how the public perceives things. If you've not been living under a Dwayne Johnson in the past 3 months, you've come across some of these graphs. Graphs like these have been the subject of 2 separate studies, the first being a joint effort by the London School of Economics and Yale, and the second being a publication by Berkeley. Both studies give one group of participants linear representations of COVID-19 data and another group logarithmic representations. The Berkeley study iterates the experiment with further controls such as educating the logarithmic group about logarithmic data. The first big problem is that subjects have varying levels of understanding of logarithmic representations, obviously typically much lower than linear representations. How the public perceives the pandemic and how they should view the pandemic is a normative or subjective comparison with not one single best answer. However, it's objectively worse to use representations the public are less familiar with, whether or not it's on purpose. The Yale and LSE study found that only roughly 41% of subjects could answer basic questions about log representations, as opposed to roughly 84% for linear representations. This is in spite of respondents of both groups stating similar levels of confidence in their predictions when using each graph to make predictions. Even if funny but alarming, it makes perfect sense, given that a previous 2001 study by Lipkus et al. Found that 16 to 20% of highly educated people answered straightforward numeracy questions incorrectly. How straightforward, I hear you ask? Well, stick around to the end of the video to see and attempt the quiz. Going back to the Yale and LSE study, they concluded that the logarithmic group was worse at making predictions. And can you blame them? The tail end truncates so many values that on its own this would be a huge problem even if the graph was understood perfectly by participants. This is a natural occurrence with the logarithmic function. If you recall at the start of the video, the more and more the logarithmic scale increased, the proportionately greater the compressions on the linear scale were. The Berkeley study found similar results. People's errors in predicting the future using both real country data and simulated data by the researchers were higher with logarithmic than with linear representations. As you might also expect, beliefs and attitudes were different as well. Those looking at the logarithmic representations across both studies have a reduced perception of the severity of the pandemic. For example, they are less likely to take precautions such as wearing a face mask and also less likely to commit to social distancing. The Berkeley publication took this even further and attempted to educate the groups exposed to logarithmic representation. While this helped reduce how relaxed some observers were about the severity of the pandemic and its risks, this group was still largely underestimating risk relative to the linear representation group. At the same time, this is also open to capture. For example, many people apply logarithms because by shrinking large numbers by proportionately more than small numbers, outliers and undesirable observations are arbitrarily attenuated. Or the fit of a regression model is improved without understanding why exactly. So even in academic fields, this tool can be misused and misunderstood. The public are generally not experts. Log representations typically mislead the public, whether intentionally or unintentionally. Logs make people less worried because they think the rate of spread is decreasing when it might not actually be the case, as Fisher's handy-dandy Fisher guide has told us. Even with the perfect understanding, the huge scale of the logarithmic graphs can make it difficult to make reasonably accurate estimations. As the public, we should always be skeptical when we see log representations and dig deeper, if not to properly understand the data, then to spot attempts to mislead us. In 2014, Cornwall suffered devastating floods. In the aftermath, the government was criticized for its lack of spending on flood defenses, and they released Exhibit A. Without realizing the logarithmic scale, one might be fooled to think flood defense spending is a ridiculously high priority. But when we remove the log transformation, as the Statistics Authority in the UK did, we see the true scale of relative spending, and the need to remain vigilant becomes clear.
Bro, come on now, dawg. Come on, man.
We've reached the end of the video, which means I owe you a quiz. Below is a table of questions from that very 2001 study I referenced on general performance on a numeracy scale among highly educated samples. The first is the base, whereas the latter portion is the extended set of questions. If you do pause the video and attempt the questions, comment down below how many you got right. Otherwise, keep watching, and in a few seconds, I will have a big reveal of the answers. So, congrats on making it to the end of the video. Go ahead and like, comment, and subscribe for more if you enjoyed. And please smash that bell button. I really love you guys, and I really need this right now, please. I'm always looking to improve, so any feedback in the comments is appreciated. Thank you for watching, and stay safe out there.